I will be correcting problem 10 from exam 1. Here's Gauss's law, which relies heavily in this problem. We can look at these three differential surfaces. We can see what's going on. There is a cube here that is emitting an electric flux density field in the AX direction right here that we were just looking at right now. So cube has 6 sides. We will take care of that later. So constant flux field, constant cross-sectional area, 1 meter squared up here. So, it would be 2 coulombs per meter squared times cross-sectional area. And then for this first differential surface, since the normal vector is parallel, this third term will be 1. For the second one, rotated 180 degrees, this third term will be -1. And for this, which lies along, let's say, the flux field, for convenience, lines, well, none of the flux field lines will actually enter or exit this differential surface, so this third term is 0. We can look at this fourth differential surface and see why. We take the projection, we match up the theta angle that is made between the normal vector, so let's say that's the right angle right there, normal vector and the incoming flux field line. We can develop an equation for the cross-sectional area of the projection of this differential surface to be this hypotenuse, delta S, times cosine of theta. And this is the dot product. We can see that we can turn these into constant values as long as we know the direction it's going in. And this differential surface will depend on the angle made with the differential normal, sorry, not differential normal, with the normal vector and the incoming field line. So this is the equation we were using above. Psi, the electric flux, is equal to the electric flux density dotted with, so dot product, differential surface. Now, we said it was a cube, correct? 6 sides in a cube. If I sum up all of these differential size, differential electric fluxes, well, this allows me to find the charge enclosed of this cube. And that's what this closed integral of d psi means, which is closed integral of this term made. We can look at divergence over here and see why volume charge density works. Well, we know Gauss's law. This is the only thing that's different, this second term of this second equation. Well, let's look at this right here, which is called the divergence of the electric flux density and why it's equal to the volume charge density. We can look at these 3 surfaces. This first one has flux field lines emanating from all points in it. We can say that the vector field of the electric flux is being spread out. This means the divergence of the flux is greater than 0. If we look at the inverse of this, all flux is converging on this second differential surface. It's not being spread out, so we can say the divergence is less than 0. For this third surface, the flux coming in the left face is equal to the flux coming out the right face, so we can say that the divergence is 0. This will have no charge inside. No volume charge, no change in the flux field due to any charge here, whether it be line, surface, volume. There's no charge there, since there's no change in the flux field. Well, we can grab all of those and make this fourth equation. And this is another way to view the divergence of the differential surface. As my differential surface goes to 0, we can see why we get a volume charge density, as we are technically dividing by another unit of measure right there. So moving on to the problem, we are given this charge at the origin and a conductive shell from 2 meters to 4 meters in the radial direction, so a sphere. We're giving its volume charge density, so how much the flux diverges from this volume. So we're given a volume, it's a sphere, we know we're going to use that. So how can I sum up the amount of charge that is sitting around inside of my conductive shell? Well, take the integral of the volume charge density dotted with dv volume, spherical coordinates, integrate correctly, 2 to 4 meters, 0 to pi on the z-axis, and then 0 to 2 pi on the xy axis. So that coincides with theta and phi, and we find 10 nanocoulombs, which would be helpful later. So now, when we evaluate this first region, we want to go from 0 to 2 meters because we want to isolate just the point charge. This will help us conveniently very much because microscopically we can think of it as this region is not touching the conductor since there's no surface charge density. So we don't care about anything outside of here. Technically, it's nothingness. So we look at inside, 0 to 2 meters. We know there's a positive charge right here. We know logically that flux field lines start at the positive charge, terminate on negative charge. There's no negative charge found. So uniformly emanates. We sub in for Q enclosed since we know quantitatively how much charge is enclosed. Use the term I mentioned before, divide both sides by it, and we get the answer. We just need to add direction component, and we understand it's in the radial direction by Coulomb's law and everything before. Now we must traverse through the conductor at some point r prime. So r prime could be here, r prime could be down here, r prime could be here. How can we develop a mathematical expression that will sum up the changing charge as we move across the radial direction through our conductor? Well, we must perform an integration over a dummy variable for our radius. So for this region, from 2 meters to 4 meters, so only this gray region, as we traverse, we must account for dq. What is dq? Well, dq is the charge inside of our volume, so we need to dot it with our volume. We need to add this extra term. So this gives us this integral. Both of those terms cancel out. And we can plug into Gauss's law again, but after we account for the second charge that is enclosed. Now, even though we are considering the region from 2 to 4 meters, we must still account for the charge enclosed at the origin. So our new charge enclosed, add 5 nanocoulombs, 5 minus 5 times 2 is equal to 5 minus 10, so negative 5. That gives us this expression. This quantitatively, this is a mathematical expression that quantitatively tells us how much charge is enclosed as we move in the radial direction from 2 to 4 meters. Now we can properly evaluate Gauss's law now that we have the charge enclosed. Technically, like let's say this blue line is our Gaussian surface at r prime. We are considering everything from the origin out now that we have added this term. So that gives us this right here, and we can check it mathematically at 2 meters. So d 2 meters is equal to 2 minus 1 meters, so 1 right here, a of our direction. Now for the last region, this is probably the simplest one. Now that we have integrated in the first step how much total charge is inside this conductor and how much total charge is at the origin, and it doesn't depend on how much we traverse radially because our Gaussian surface encloses all of it, we can do the simplest version of Gauss's law right here, where we add up the charges and just divide by our differential surface, our constant differential surface, which is just 4 pi r squared as we traverse radially from this 4 meter boundary and on. That's what all of these areas were. That's what all these r's are for and why it falls off at that rate. So we could say from here to here, there's a fall off of r squared, depending on what we choose our Gaussian surface to be. But it would still apply since we are evaluating from 0 to 2 meters here, 2 meters to 4 meters here, and greater than 4 meters here. And again, continuity, because we have no surface charge density, only volume. At 4 meters, it will equal 15 nanocoulombs divided by 4 pi r squared in the radial direction. 15 nanocoulombs divided by 4 pi r squared in the radial